All right, this is AP BC Calculus. We're doing a BC only section. This is Unit 10, Section 6. We're talking about comparison tests for convergence. So basically, we're going to learn two tests here, direct comparison, or just the comparison test, and the limit comparison test. In both of these, you are comparing the series that you are given to a known series, like a series that you know the behavior of, which means you're usually comparing to either a geometric series or the p-series, right? Specifically, also sometimes one of the two p-series that we separately memorized, which are the harmonic and alternating harmonic. But again, we are very routinely going to be comparing these to some of those other series that I told you have to memorize the behavior of, right? So it's important to understand how geometric and p-series work because other problems, like other convergence and divergence problems, are going to lean on that knowledge, right? So we need to make sure we have that base knowledge memorized. All right, so here's what the comparison test says. Sometimes you'll also hear it called direct comparison. So suppose you have some infinite series, you're summing a sub n, and you want to know if it converges or diverges. Notice here we're not even bothering to say starts at n is 1 and ends at infinity. We get that it's infinite. We don't really care if it starts at 1 or 2 or 3 because those first couple finite terms don't really matter. So you're going to choose some other series, b sub n, that you know the behavior of, right? So like a geometric series or a p-series. If b sub n, the one that you picked, converges and is larger than a sub n, then a sub n also converges because smaller than a finite sum is also finite. Now, a caveat about that smaller is that you want all of these functions to be greater than 0. So by smaller, we mean closer to 0, not more negative, right? So if a sub n is smaller than b sub n, and we know that b sub n is a finite sum, then smaller than finite also has to be finite. Similarly, if you picked a b sub n that diverges, and your b sub n is smaller than a sub n, well, if b sub n diverges, it means it's infinitely large. If a sub n is bigger than infinitely large, it must also be infinitely large, and thus must diverge. So, in the simplest of terms, remember that divergent equals infinite and convergent equals finite. That's an easy way to kind of compare this. So, very, very often we're going to be comparing to a p-series where either the numerator or denominator has a constant added or subtracted. So let me show you what I mean by that. So the vast majority of the time when you're choosing a series for comparison, either direct or limit comparison, what you're going to do is you're going to look at a given series and pretend that only the leading terms matter. So I'm going to pretend that all I care about is the n squared over the 3n to the fourth, and I'm going to say, oh, that would be a 1 over 3n squared. I would try to compare this to 1 over n squared, right? Because I'm going to look at those leading terms, right? Same thing here, right? If I look at these guys, I recognize the leading term is an n over an n squared root n. So I'd say, oh, that's an n over, that's an n to the second and an n to the 1/2, right? So that's an n to the 2.5 or an n to the 5/2. I would recognize that this behaves like a 1 over n to the 3/2. That's what I would try, right? I would try 1 over n to the 3/2 for my comparison. When I look at these, I'd be like, oh, hey, I'm going to pretend like only the leading term matters. That would behave like a 1 over n, so that's what I would try. I would try 1 over n, right? If I were looking at these guys, I'd look here and say, oh, I pretend I only care about the leading terms. I would try 1 over n as my comparison. So I'm saying that's a good place to start. I'm not saying, so sometimes you can do direct comparison, sometimes you're going to have to do what we call the limit comparison test, but in either case, most of the time when you're given one of these, the thing you're going to be comparing to is the p-series you would get if you just pretended only the leading terms existed. And that's a decent sort of place to start. Okay, we're going to use the comparison test to determine if the series converges or diverges. So again, what I'm going to try is I'm going to try what would happen if I had a root n on top of an n, which is an n to the 1/2 on top of an n to the first, or a 1 over n to the 1/2. So I'm going to try to compare this, because this is a p-series that diverges. So, right, this is a p-series that diverges because p is less than or equal to 1, right? So it's a p-series that diverges. So I'm going to try making this my b sub n, right? So here's what I need to show. To do the direct comparison test, or just the comparison test, right, what I need to show is that since I know, right, it is known that the sum from, I think they started at 2, so the sum from 2 to infinity of 1 over n to the 1/2 diverges. So if I can show that this sum, or that if I can show that this thing is bigger than this thing, it must also diverge, because bigger than divergent must also be divergent, right? If you're bigger than something that's infinitely large, you must also be infinitely large, okay? And so I'm trying to show it's bigger, right? So let's see if I can show that, right? Let's see if I can show that. So if I clean this up a little bit, I could actually rewrite this guy to look just like this. I could say, oh, so what I'm trying to show, right? So I know that this is what I have. This is my b sub n, right? I could multiply that by root n over root n and get this, right? So this is my b sub n. The question is this bigger than this, right? Well, and the answer is yes, because a smaller denominator, right, n minus 1 would be a smaller denominator, means a bigger fraction. Right? See how the numerator, so the numerators are equal. Numerator equals numerator, right? Same numerator. A smaller denominator means a bigger fraction. So I know that this thing is bigger than this thing. I know that this thing diverges. So by direct comparison, this sum from n is 2 to infinity diverges, because it's bigger than something else that diverges. This is definitely where these problems get harder. So one of the places that you're going to see this is on what we call multiple choice, where I give you 3 series, Roman numeral 1, 2, and 3, and say which of the following converge. And of the 3, one of them is very likely a p-series, and one of them is very likely geometric. So then there's only one that's harder, right? And that harder one might be an integral test, or it might be direct comparison like this. But you're going to have to figure out whether that one converges or diverges, because usually that's the one that makes the problem, right? And we can do some examples of that. But let's go ahead and do another practice problem like this. So we're going to use the comparison test to determine if this converges or diverges. So remember, the first thing I want you to do is I want you to think, what probably a p-series could I compare this to, right? So what your brain's going to do is you're going to pretend that only this matters, and you're going to say, oh, I'm going to use my b sub n as 1 over n squared. I know that this is a p-series with p equals 2. Since 2 is bigger than 1, this thing converges, right? So if this a sub n, right? So if a sub n is positive and less than b sub n, since this converges, this has to also converge, because smaller than something that converges is convergent. Well, is 1 over n squared plus 1 less than or equal to 1 over n squared? And the answer is yes, right? Because see how the numerators are the same? Bigger denominator means smaller fraction. Right? So bigger denominator means smaller fraction. Check. This is true. So since this converges, right? So since this converges and this value is smaller than this value, right? This whole thing was my a sub n. Since 1 over n from 2 to infinity, 1 over n squared converges, and 1 over n squared plus 1 is less than or equal to 1 over n squared, and both of them are positive, on this window from 2 to infinity, right? By direct comparison, this sum from 2, I think it was 2, it might have been 1, it doesn't really matter. Oh, it's 1, fine. 1 to infinity also converges. Now, if you're somebody who absolutely hates when I do this logic thing, like if this is breaking you, if you're like, Hogan, I can't just conceptualize if something's bigger, you could check. You could say, hey, is this thing, when is this thing equal to this thing, right? And you could cross multiply and you'd get n squared. Well, they're never actually equal. You want to say, when is this thing less than, sorry. We know that the n's are all positive, right? So you could say, when is this thing less than or equal to? And you could multiply essentially over, right? You could get 1 is less than or equal to a 1 over n squared times this n squared plus 1, right? And then you could multiply this guy over. You don't have to flip the sign because this is positive and this is also positive, right? So you'd get n squared is less than or equal to n squared plus 1, right? When you subtract the n squared over, you get 0 is less than 1, which is literally always true, meaning that this statement is definitely true. Like if you need a mathier way to see that, you could definitely figure that out. But I think it's absolutely fine to be able to conceptualize that this thing is smaller. If that's not something that you feel like you can do, you can actually say this and then say, is this true? And you could solve, right? Okay, so we're going to go ahead and use the comparison test again, right? So I'm going to look at the leading terms, right? I'm going to recognize, to pick my b sub n, I'm going to look at what the square root of n to the 4th over n to the 5th looks like. Well, that's an n squared over n to the 5th, which is a 1 over n cubed. So this is what I'm going to try and use as my b sub n. I know that this converges because it's a p series where p is greater than 1. So I know this converges. Once I know it converges, it's my job to show that a sub n is smaller than b sub n because I just saw that b sub n converges. So the question is this thing, sorry, that's a 4. The question is this thing, so we can definitely see it's positive, right? The numerator is positive or 0, like the very first term is 0, but so, and the denominator is definitely going to be positive because all the n's are positive. So definitely greater than or equal to 0, that part's easy. The question is this thing smaller than this thing? And there's a couple different ways to do this. I'm probably going to cheat and just write, I'm going to write this as this version that already looks like this. And the answer is yes for 2 reasons. Number 1, a smaller numerator, right? Smaller numerator makes the fraction smaller. And at the same time, a larger denominator is another factor that makes something smaller. So a larger denominator makes a sub n smaller. So a sub n is definitely physically smaller. So the answer is yes, this is true. So by direct comparison, or by the comparison test, this thing converges. Again, you're not going to see a ton of these as free response. Most of this is multiple choice. So most of this, in fact, is the multiple choice, where you're given like 3 series and you're asked to figure out which of the 3 converge or diverge. And we'll do a couple examples of that in a minute. One of the reasons we haven't done a bunch of examples of that is you don't know everything you're supposed to know yet. All right, so use the comparison test. So go ahead and give it a try, right? So again, to find your b sub n, look at the leading terms. So I'm going to guess that b sub n is probably this thing, which I know diverges because it's the harmonic series, right? So its p is 1, it's called the harmonic series. So I know it diverges, so what I need to show is I need to show that that b sub n that I have here, which I know is divergent, is smaller than a sub n to show that it is also divergent. So the question we have to ask ourselves, you can see that they're definitely both positive. Notice that I started at n is 4 because that would definitely mean that the bottom is clearly positive. So anyway, so they're definitely positive, right? So we, and I could have started at a smaller number than 4, but it doesn't matter. So definitely true that they're both positive, right? The question is, can we show that n squared over n cubed is smaller than n squared over n squared minus 3? And the answer is yes, we can, because a smaller denominator means a bigger fraction, right? The numerators are the same, right, which is not accidental. So the numerators are exactly the same, and the smaller denominator means a bigger fraction. So by direct comparison, this thing diverges, right? Because bigger than infinite is also infinitely large. All right, so this one we've actually seen before. We've seen it with the integral test because sometimes many different tests get you the same answer, but I just wanted to walk you through this anyway so that you'd see this, okay? We're going to use direct comparison, right? So in this case, right, I'm going to compare, this time I don't have a leading coefficient, but I'm going to see, I see there's an n on the bottom, so I'm going to try 1 over n, which I know diverges, right? So 1 over n diverges, it's the harmonic series with p equal to 1. So I say, okay, I know that my b sub n is 1 over n, right? Since this diverges, I want to show that this thing is bigger than 0, which 1 over n is for n values starting at 1, obviously, and that a sub n, the thing I was given here, is bigger than that, right? So this thing is my a sub n. Well, I know that they're all positive, so the question is natural log of n over n bigger than 1 over n? Well, the answer is yes, because natural log of n is definitely greater than 1 for any n values greater than e. Now, you might say, okay, Hogan, so you might say, wait, e is like 3-ish, and we're starting at n is 1. Is that okay? Well, yeah, because remember, the first couple terms, so this still diverges, right? Because those first few finite terms, right, those first few terms don't change the behavior of the entire infinite series, right? The 1 or 2 terms at the beginning, or 3 or 4 terms at the beginning, or even 50 terms at the beginning can't change whether this thing sums to an infinite value or a finite value, because at the beginning you have a number of finite terms. Well, adding or subtracting finite terms will not change an infinite value to finite and will not change a finite value to infinite. So those first couple of terms don't change converge or diverge behavior. So the answer is yes. By direct comparison, this thing diverges. Because again, we are looking at a function that is bigger than a known divergent series. But to do this, you have to know some of those divergent series. You have to look at 1 over n and think, hey, you're the harmonic series and you diverge, right? That's important information. All right, cool, moving on. All right, so the limit comparison test is similar to the direct comparison test or to direct comparison. So suppose you have this same infinite series, right, the sum of a sub n from whatever finite value, like 1 to infinity or 10 to infinity. And you want to know if it converges or diverges, right, where a sub n is positive, right? So you choose a series, also positive, with known behavior, like a geometric or a p-series, right? If the limit as n approaches infinity of a sub n over b sub n is equal to some constant that's positive, non-zero, then nc is finite, right? Then they behave the same, right? So that is, if the series that you chose converges, then a sub n also converges. If the series you chose diverges, a sub n also diverges. So you usually end up using this when you can't use the direct comparison test for one of 2 reasons. Either you can't find a series that does what you want and is either smaller or bigger, depending on if you want convergent or divergent, etc. Or there's more than one constant added or subtracted to the top or bottom of a fraction, so it's hard for your brain to conceptualize whether the function is larger or smaller. Okay, so we're going to use the limit comparison test to determine whether this series converges or diverges. Now, I don't actually have to use the limit comparison test. Well, I do, actually, I lied. So I would want to compare it to this, right? That's my guess, right? So my guess is that my b sub n is going to be 1 over n squared, which I know is a p-series that converges, right? Because p is 2. So I want to show you why you can't use direct comparison here. It's not now I understand that this exact example I told you to use limit comparison, but the reason it's not direct comparison is because 1 over n squared minus 1 is bigger than 1 over n squared, right? Smaller. So bigger than finite is not something we know the answer to. Bigger than finite could be finite, bigger than finite could be infinite, we don't know, right? So that's not helpful. I can't use direct comparison. So since I can't use direct comparison, I'm going to do the limit as n approaches infinity of my a sub n over my b sub n, right? And if this comes out to be a finite non-zero number, then they behave the same. So that's the limit as n approaches infinity of a 1 over n squared minus 1 times an n squared over 1. Well, that's going to be the limit as n approaches infinity of n squared over n squared minus 1. We know that we only look at the fraction of the leading coefficients when the degrees are the same, so that's a 1, which is a finite non-zero number so they behave the same. Right? So that's what this tells me. They behave the same. Since I know that the series I picked converges, then this series must also converge. So again, the reason you do limit comparison, and you're never really going to be asked to do limit comparison specifically the way I've done here in this example. You're just going to be asked if something converges or diverges, and you're going to have to go through a checklist in your head to figure out which one it does. In general, limit comparison is a good option when direct comparison doesn't work because of one of the issues I listed. Because, for instance, in this case, bigger than finite isn't helpful to me, right? All right, so go ahead and try this. Again, you're going to do a limit comparison test. So the fast way to pick your b sub n, right? So I'm going to pick that my b sub n. Honestly, you could either do it as a 4 over n, right? Or you could just look at the leading terms and recognize that it's the 1 over n you care about. Or you could put a 4, it doesn't matter. Or you could do 4 over n, it doesn't matter, right? So I know, either way, I know this diverges, right? This diverges because it's a p series where p is 1, right? It's the harmonic series. So since I was told to use limit comparison, I can basically just skip to it if you want. The reason here that it's not easy to do direct comparison is because it's tough to show. See how these are fairly complicated with the plus or minus, like you're adding a 9 on the bottom, but you're subtracting n on the top. So tough to show if this is bigger or smaller. And if you did actually figure it out, like the bigger denominator means smaller fraction, the smaller numerator means a smaller fraction, you're actually going to get that this is a smaller number, right? You're going to get that this would be smaller than this. But this is an infinite thing, and smaller than infinite is not helpful. Like smaller than infinite could be infinite, it could be finite, I don't know, right? Smaller than infinite is not helpful. So I can't use the direct comparison test. Again, I wasn't asked to. I was asked to do limit comparison, but I just want to point out that when you're doing this, you're not expressly going to be asked normally. You're going to have to figure out which test works best for you. So I'm going to go ahead and put this thing. And I don't know, I guess we can pick this one if you want. Like we can do this, doesn't matter. So 4n squared minus n over an n cubed plus 9. And on the bottom, I'm going to have a 4 over n. So that's going to be the limit as n approaches infinity of 4n squared minus n over n cubed plus 9 times, and when I flip this, instead of being 4 over n, it's going to be an n over 4. So I'm going to get that this is a 4n cubed minus n squared over a 4n cubed plus 9n. Limit as n approaches infinity. And again, if you had wanted, you could have just picked a 1, right? Like you could have picked 4 over n, or you could have picked 1 over n. It doesn't matter. So when I look at these two, I say, oh, look, as I approach infinity, I only care about the leading terms since they have the same degree. This is going to be a 4 over 4 or a 1, which is a finite non-zero number, so they behave the same. So they behave the same, which means that since I know 1 over n diverges, this guy must also diverge. All right, so limit comparison test again, right? Again, to pick my b sub n, I'm going to look at the leading terms, right? So for my b sub n, I'm going to choose, and again, you could either do it with the 2, or you could just look at the numbers. It's fine, right? So this, if I only look at the leading terms, this is an n to the first over an n to the 3 halves, or a 1 over n square to the 1 half, my bad. So 1 over square root of n. So this diverges, because p is 1 half, right? The number is less than or equal to 1. So I know this diverges. If I jump right into the limit comparison test, right, because they specifically told me to use the limit comparison test, I can say, hey, 2 plus 1 over n, this is an n cubed plus 1, divided by a 1 over, and you could make it a square root of n, or you could make it an n to the 1 half, it really doesn't matter. So this is going to end up being the limit as n approaches infinity of a 2n plus 1 over this square root of n cubed plus 1 times, and then a square root of n over 1, right? And if you clean this up, and again, it really doesn't matter how you do it, I'm going to end up getting that this is a 2n to the 3 halves plus an n to the 1 half. And on the bottom, I have this the square root of n cubed plus 1. So again, I really just want to look at the leading coefficients as n approaches infinity, and they're both an n to the 3 halves. So I end up getting that this behaves as a 2 over 1, because that's the coefficient is the square root of like 2 over square root of 1. That's a 2, which is a finite non-zero number. So they behave the same. And since I already know what my b sub n does, right, because it's that p series, so it diverges, right? So this one also diverges. And that's how limit comparison works. So let's go ahead and do one more like this. And all right, so again, when you're trying to figure out what to compare to, look here, right? So I'm going to pick my b sub n as n squared over n to the fourth, which is a 1 over n squared. Now, I know that this converges because it's a p series with p is 2. So if I do the limit comparison test, the limit as n approaches infinity of this crazy monstrosity divided by a 1 over n squared, right? That's going to be the limit as n approaches infinity of n squared plus 2n plus 1 over n to the fourth plus n squared plus 2n plus 1 times an n squared over 1. So when I distribute, I'm going to end up getting the same situation I've had a bunch of times now, right, where that leading coefficient is going to end up having, or the leading term is going to end up having the same degree as the denominator, squared plus 2n plus 1. These are what I care about. That's a 1, right, 1 over 1, so which is a finite constant greater than 0, so they behave the same, which means if I know that this one converges, then this one also converges. So notice that all of this is built on memorizing if a p-series converges or diverges, and so I really wasn't kidding when I said it was super important you memorize those p-series. All right, so let's do a multiple choice. We're going to do an E6 and a P6 just to show you what this looks like. So this is sort of like a sample AP question. Be very careful to read which thing they're asking. Sometimes they ask converge, right? So sometimes the AP says converge. So you have to make sure you know what you're looking for. So underline it, pay very careful attention, and say, oh, this one says diverge. So when you do these, you want to start, so you look at the 3, start with the easiest. Okay, see if there's one that is straight up a memorized series, okay? So the first thing I notice is I say, wait a second, this is the alternating harmonic series, right? It's got the plus 1, minus 1. This converges. So I cross off 3 because they said what diverges. So instantly, I can cross off several answers, right? So now, because all of those have answer 3, right? Because alternating harmonic converges. Next thing I'm going to do is I'm going to look at these two, right? Now there's 2 ways to think about this, right? Honestly, since I'm down to it just being 1 and 2, like 1 only and 2 only, I just have to look at any one of them, right? So I'm going to look at 2, and I'm going to recognize that the nth term test tells me this diverges, right? If I look at the limit as n approaches infinity of a 3n squared plus 5 over a 10n squared plus 7, I get 3/10, which is not equal to 0. So this thing has to diverge. This one has to diverge, which tells me it's got to be B because there's no other option, right? Because what's essentially happening is for huge n, right, I'm just adding 3/10 forever. That's what's happening for these big values. So that's obviously going to be infinitely large. If you were trying to figure out if this this guy converges or diverges, so at that point you're done. But if you still wanted to look and figure out 1, right? So for 1, so I already know the answer is 2 only based on the order I did this. But if you wanted to do it just to show you how, right? Just to review how we would do 1. If we were looking at this, I think it starts at 1 and goes to infinity, and I think it was an 8 over an n squared plus 2. 8 over n squared plus 2. I would compare this, so I would look at this, and I'd say, oh, let's look at b sub n is just an 8 over n squared, which I know converges because it's a p series with p is 2. 8 over n squared plus 2 is smaller than 8 over n squared because bigger denominator means smaller fraction, right? Bigger denom, right? Bigger denom is smaller fraction, right? Smaller number. So by direct comparison, this thing converges, right? Because smaller than convergent is also convergent. And that's it for this. Oh, I'm sorry, that's it for E6. Let's do a P6. My bad, my bad. All right, so same thing. I want to know which of the following diverge, right? So again, diverge, be careful. All right, so I'd start with the easiest ones. I look at this and I'm like, oh, hey, this is a P series, right? This is a P series. P series are pretty easy. This is a 7 over an n to the 1/3. That diverges for sure because P is 1/3. So right away, I know that my answer should involve a 1. So I cross off any answer that doesn't have a 1. Great. I look at this guy and I say, oh, hey, this is geometric, right? This is geometric with r equals 2/3. So that should converge. Okay, so I want answers that don't involve 2. Great, it's not this one. So really, my entire problem comes down to whether number 3 converges or diverges. So I'm going to use my b sub n as 6n over n squared, or just a 6 over n. I know that diverges because that, like, so this piece diverges, right? So I know that this piece diverges. And then if I want to compare, right, so 6n over n squared minus 3 compared to 6n over n squared, well, unfortunately, so bigger denominator, right? If you make the denominator, smaller denominator, bigger fraction, right? So this thing, right, the denominator is smaller, so smaller denom equals bigger fraction, right? So this thing's bigger than this. Well, I know 6 over n diverges because it's a P series where P is 1. So bigger, right, bigger than infinite also means infinite, so this thing diverges. And once I know that, it's answer E, right? So that's kind of the idea. You should start with the easy memorized ones first, and that's the plan. So that is it for 10-6.